right, I don't know if anybody has joined yet. We will start the presentation. So in today's presentation, we'll look at comparing means or proportions. How should I analyze my data? So in today's presentation, we'll discuss the scales of measurement. We'll define measures of central tendencies, such as mean and median. And we'll describe the measures of dispersion or variability, such as standard deviation, standard error. And we'll describe proportion, and we'll discuss how to determine when to use means or medians or proportion. So when we say scales of measurement, based on the procedures of measurement and inherent characteristics of the variable, a variable is classified into different scales. And these scales are very important, especially when we determine how to analyze our data. So a variable can be ordered. So one level is higher than the other, or there is an inherent ordering or ranking in the data, like when data is collected on whether a person agrees or disagrees about something on Likert scale, that kind of data is ordinal on ordinal scale. So the items are ranked or ordered, and such data are called ordinal scale data. So these examples are for behavioral surveys. So, for example, after a class is given, an instructor might ask how the students like the class, and their responses might range from like agree, disagree, strongly agree. So for example, the instructor might say today's presentation or today's topic is important for my future study, and the students might react by selecting whether they agree to the statement or whether they disagree to the statement. And such data, where there is an inherent rank or ordering in the data, is called ordinal scale data. So the other type of data is nominal scale. This is used for categorical variables. There is no ordering among the labels. Such variables are like gender, male, female, and color, religion, region, and many other categorical variables. There is no ordering. There is no difference between the labels. There is no like male is better than female or greater than the other. There is no ordering, inherent ordering. Such type of data are on the nominal scale of data. The other scale of measurement is interval scale. The interval scale is for numerical scales in which intervals have the same meaning throughout. The only problem with this type of data is that there is no true zero. The best example is a temperature scale, such as Fahrenheit scale of temperature. So in Fahrenheit scale of temperature, the freezing point is 32, is arbitrary, and the boiling point is about 212. And temperature can go into negative. And 0 degree Fahrenheit doesn't mean there is no temperature. And so that's what we mean by there's no true zero. In addition, it doesn't make sense to say 70 degree Fahrenheit is twice as hot as 35 degree Fahrenheit. The ratio scale is the most informative scale. Again, it's just like the interval scale is used for quantitative measurement. It's a scale with additional properties. It's an interval scale with additional properties that 0 means the absence of a quantity measured. So for example, for the temperature, when the temperature is measured on Kelvin scale, the freezing point for water is about 273.15, and the boiling point is about 373.15. And there is a true zero, and a true zero on Kelvin scale means there is no movement of molecules. And so there is no true zero in that case. Examples of variables with ratio scale are like blood pressure. Blood pressure in a person with hypotension, the blood pressure can be 0, and 0 means there is no like movement of blood, and so it's a true 0. Cholesterol, length, and the likes. And in case of the ratio scale, 60/20, which is 3, is twice as 30/20. So one ratio is twice as the other in this case, and that information is so informative, unlike in the interval scale. Like when we say it, 75 Fahrenheit is not twice as hot as 35, but in the ratio scale, ratios have properties which are useful and can be interpreted. The interval scale or ratio scale measures of continuous variables. So the measures of central tendency is the statistical measure. Central tendency is the statistical measure that identifies a single value that represents or is representative of the entire distribution. The measures of central tendency are statistics used to summarize average. They include the mean, median, and mode. So there are different types of means. The most common one is the arithmetic mean. But the other types of means are the weighted mean, geometric mean, and harmonic mean. Like I said, the most commonly used one is the arithmetic mean, and it's simply also referred to as mean. And it's the sum of all the observations divided by the number of observation, the sum of all the quantities. For example, one person might have a systolic blood pressure of 130, another might have 125, and another might have 90. The sum of all those observations divided by the number of participants or sample in the data, that gives us the arithmetic mean. The geometric mean is the arithmetic mean of the values on log scale, converting the values into logarithmic scale. Or it's the nth root of the product of the values, multiplying the values and taking the square root of the nth root of that product gives us the geometric mean. The harmonic mean is the reciprocal of the arithmetic mean. This is calculated by taking the reciprocal of a given observation. So we will sum the 1 over the observation and divide that by the number of observation. That gives us the harmonic mean. And the weighted mean is used when some values are more important than others, and so we will multiply by the weight given for each individual, and then divide it by the total weight, and that gives us the weighted mean for the observations. So the arithmetic mean is the average of a continuous data or a quantitative measurement. It's the sum of all quantities measured divided by the number of observations. The advantage of the arithmetic mean is it takes all values into account. So this is especially as compared to the median, which is the middle observation. The mean takes into account all the values. The disadvantage of mean is it is influenced by extreme values or outliers. And most of the time it does not appear in the data. Another disadvantage of the mean is that sometimes it doesn't appear in the data because it is created based on all the observations, but it might not be there in the data. It may not be used for ordinal data as well. The median is another measure of central tendency at the middle of observation in an ordered quantitative data when the number of observation is odd. So when we have an odd number of observation, when we say that if the number of participants is say 21 or 25 or 27, it's not divisible by 2. That number of observations is not divisible by 2. And that is what we mean by odd. So when the number of observation is odd, the median is the middle observation in an ordered quantitative data. So ordering is very important, and the median is the middle one. When the number of observations is even, the median is the average of the two middle numbers when the number of observations is even. So for example, if the data is 1, 2, 3, 4, 5, the median is the third. So we have here 6 observations. The number of observations in this data is 6, and the middle ones are the ones on numbers 3 and number 4s, and they happen to be 3 and 4. So dividing those on number 3 and number 4, it gives us 3.5. So the median is 3.5. Again, the median is not an actual data in the original data. That shares a similar characteristics with the median, with the mean. So the median is not affected by an extreme values. We might add, say, 200 as the end here, and replace 5 by 200. The median remains the same. It's not affected by extreme values. We might also add a huge negative number, negative 1,000 instead of 1. The median remains again 3.5. So the median is not affected by extreme values. The mode is not commonly reported or used as the most frequent number among the observations. For example, the mode of 0, 2, 3, 4, 4, 4, 2, 7, 8 is 4. The data might have no mode. That means no number is repeated. It might have one mode, like in this case, we have 4 as the mode, or the data might have multiple modes or multiple equally repeated data points. So in this data, in the second data, 0, 1, 2, 2, 2, 3, 4, 5, 5, 5, 6, both 2 and 5 are repeated 3 times, and they are the mode. So when we look at how to summarize quantitative data, the decision depends on 1, the distribution of the data, 2, the scale of measurement, 3, what we want to, like the message that we want to put out. So for example, if a coach wants to scare the opponent team, the opposite team, by the height of his players, the coach might report the extreme values, and the coach might report the median. For example, if the coach has quite a few players with long height, say 6 feet, 7 feet, but most of the players are say 5.7, 5.8. The coach might want to report the total, so the coach might want to report the median because most of the players have a low height, so the coach might want to report the median to scare the opposite team. So based on the message that you want to put forward, you might want to use median or the mean. The other important thing is the distribution of the data. So when we say distribution of the data, we have a normal distribution where the data has the data is symmetric around the mean, and there are no much extreme values, and the data are within about 2 standard deviations from the mean. And when we plot the data on a histogram, we will have a bell-like curve shape of the data. So whether to summarize using mean or median depends on the distribution of the data. When we use mean to summarize normally distributed data. One way to check whether a data is normally distributed is by plotting normal quartile plot. So on the x-axis, there is theoretical data that's normally distributed, and we compare our data to that theoretical data based on the measures of central density of that data. So when we compare, if the data point is from the actual data, our data lies straight on the line, like in this case, the data is said to be normally distributed. If the data deviates a lot from the straight line, as in this figure, the data might be like dispersed all over the places. In that case, the data is not normally distributed. So if the data is not normally distributed, we would rather report the median than the mean. So we summarize non-normally distributed data or skewed data or data with outliers using the median, but data that's normally distributed and come from a normally distributed population will report the mean. And the other requirement or criteria of selecting whether to report mean or median is based on the scales of measurement. So for ordinal data, for data that has an inherent order, usually, like for example, a pain score that ranges from 0 to 10, would rather report median than the mean. So this is again another way to look at whether the data is normally distributed or not. So normal distribution, we say, is one of the methods to decide whether to use the mean or the median for summarizing the data. So in the first case, is again quantile plot for cars, carburetors, long time ago, before the modern cars. Cars used to have some kind of barrels based on the number of cylinders, and so this is it ranges about like 2 to 6, and so these are the quartiles of the carburetors. And on the x-axis we have the theoretical distribution for the data. And in this case, as you see, the data doesn't lie straight on the straight line. It deviates from the straight line and it's not normally distributed. So for this kind of data, like the old carburetors, we will use the median to report the measures of central tendency. Again, this is for the same data, plotting the histogram with the normal curve. We see that there are skewness towards the right. There are outliers towards the right. Most of the data are on the lowest low side, around 1 to 2, and again, to some extent around 4, but there are some extreme data like around 6, around 8. And so for such kind of data, we not use the mean to summarize the data. So we'd use the median to summarize such kind of skewed data or non-normally distributed data or ordinal data. So variables on ordinal scale are summarized as median and interquartile range. Variables on ordinal scale, like pain score, in other similar scores are summarized as median and interquartile range. So when we say interquartile range, it's one measure of dispersion, data dispersion or data variability around the measures of central tendency. So variables in interval and ratio scales are summarized as mean and standard deviation, or as median and interquartile range based on their distribution. And categorical variables and ordinal variables are summarized as categorical variables are summarized as counts and proportion or percent, while variables on ordinal scale are summarized as median and interquartile range. So usually we don't only report the measures of central tendency alone. We supplement that by other statistics that tell us about the variability of the data around the mean or around the median. So the measures of variability or dispersion include the standard deviation, standard error. Also, we use confidence intervals and interquartile range. So the standard deviation is the square root of the difference between a given observation, the sum of the difference between a given observation and the mean of that sample, divided by the number of observation minus one. Minus one is due to the degrees of freedom. Like we need to determine other values, we need like we can use n minus one observations, where n is the number of observations, x is each observation, and the x bar is the sample mean. The standard deviation tells us how straight the data are around the mean. The calculation of standard deviation assumes normal distribution, like we said, and the data has to have a bell-like curve with a lot of the data in the middle and very few on edges or on the extremes. And the standard deviation, like the mean, is also impacted by outliers or extreme values. Because the mean and the standard deviation take into account extreme values for non-normally distributed data, it's not a good idea to use the standard deviation and mean to summarize. So let's calculate the standard deviation of for the data, a simple data 1, 2, 3, 3, 4, 5. So the sum is 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 9 is plus 5, 18. And the number of observation is 1, 2, 3, 4, 5, 6. So 18 divided by 6 is 3. The mean is 3. And the standard deviation is the difference between each observation, 1 minus the mean, 3, the whole square, 2 minus 3, the whole square, and that gives us divided by the number of observations minus 1, which is 5, that gives us 2. So the square root of 2 or 1.4. The interquartile range is usually used with the median. It's reported when the data is on ordinal scale or for a non-normally distributed data. And it is the difference between the data value that holds 75% of value below and 25% below them. For even data points, the quartile 1 is the median of the lower half. So the data point that holds 75% below itself is the quartile 3, and the one that holds 25% below itself is the first quartile. And for even data points, the first quartile is the median of the lower half of the data. So if we have 10 data points, the first five lower data is the one that we are referring to, lower half here. So Q1 or quartile 1 is the median of the lower half, and quartile 3 is the median of the upper half. And if there are odd numbers of data points, so for example, 9 data points as in this example, 1, 2, 3, 4, 5, 6, 7, 8, 9. The calculation of the quartiles are based on the following. So if there are 4 times n plus 1, so for example, 4 times 2 plus 1 is 9, as in this case, data points, the first quartile is 25% of the second value plus 75% of the third value, which is n plus 1. And the third quartile is 75% of 3 times n plus 1's value plus 25% of the 3 times n plus 2's value. So in this case, we have 9 data points. There are 4 times 2 plus 1, or 9 data points. The n is 2. And the first quartile is the 25% of the second value. 25% of the second value. And the second value is 2 in this case. And plus 75% of the third value. 0.75 times third, and so the first quartile is 2.75. Third quartile is the 75% of the 3n plus 1, or the seventh data point in this case, 1, 2, 3, 4, 5, 6, 7. So that is 0.75 times 6 plus 0.25 times the second data point, which is 7. And so the third quartile is 6.25. The interquartile range is the difference between these two data points, the third quartile and the first quartile. So in this case, it's 6.25 minus 2.75, or 3.50. If you understand how to calculate the interquartile range in the normal situation and don't have to calculate it by hand, you can use softwares which easily provides you the interquartile range. So outliers are other phenomenon where there are extreme data points. Extreme data points, they can sometimes be a real data point. Other time they might be invalid data points. When we do data analysis, we have to look at the distribution of the data. If there are 2 extreme values, we have to ask, are these data plausible? Can they be real, or there is entering error? And we have to differentiate. So there are, again, software provides you the outliers in the data easily. But the way to calculate the outliers, to know the outliers are, they are the values which are less than the first quartile minus 1.5 times interquartile range, or they are greater than the quartile 3 plus 1.5 times interquartile range. So in the data 6, 7, 15, 6, 39, 40, 41, 42, 43, 47, 80, 80 is an outlier because it's greater than 42.75 plus 1.5 times 22.50. If we calculate the third quartile, it's 42.75, and the interquartile range is 1.5. The interquartile range is 22.5, and the 80 is greater than this value. The value is greater than the Q3 plus 1.5 times interquartile range. In this case, 80, a value, if we observe such value, we say 80 is an outlier. So if it doesn't give any meaning for the data, if it is invalid, we might want to remove that data, or we might change how to analyze the data. So again, whether we should compare means or median depends on the type of the data, whether it is on ordinal scale, ratio scale, interval scale, or whether it is categorical and the data distribution, whether it is normally distributed or not. For ordinal data and non-normally distributed data, we compare medians or ranks. And for normally distributed continuous data on interval or ratio scale, we compare means of the different groups. For proportions, we report frequency, how frequent the data is. For example, if the data is about gender, we report the number of male participants in the study and the number of female participants in the study with the proportion. So out of 100 participants, maybe there are 55 female and 45 male, and the proportion is 55% female in the hypothetical data. So frequency, proportions, and frequency are used to summarize nominal, scale, or categorical type of data. Continuous variables can also be converted into categorical variables based on some criteria. For example, age below 55 and above, greater than or equal to 55 as categorical data. BMI, for example, is a body mass index is, for example, reported as normal, BMI, overweight, obese, and the likes. But normally, BMI is a continuous data. It's found by dividing the weight in kilogram over height in meter square. The standard deviation for proportion, just like in means and for the interquartile range, we also calculate the standard deviation for proportions. And it's always important to know it's not good enough to only report the point estimate for a given data point. We have to supplement the measures of variability, such as the standard deviation. So the standard deviation for a proportion in a binomial distribution is calculated as square root of a proportion that we are interested in times 1 minus the proportion, where usually if they say, for example, if the proportion of patients that recover of coronary heart disease in a population is 80%, the standard deviation can be calculated by 0.8 into 1 minus 0.8, which is about 0.4. The standard error for the proportion is the standard deviation divided by the square root of the sample size. So for the above proportion, the standard error is about 0.057. And the standard error is used to calculate the 95% confidence intervals. So the 95% confidence interval for the proportion of the coronary heart disease patients who recover like this is a hypothetical data, but 0.8 plus or minus 1.96. The 1.96 comes from the 95% confidence interval. It's a quartile on the normal scale, and times the standard error, which is 0.57. And we have the proportion of those who recover from coronary heart disease ranges from 0.69 to 0.91, and the 0.80 lies between the two numbers. So it's not always good enough to report only the point estimate, which are like the mean, the median, or the proportion. It's important to report also the variability around the point estimate, like the standard deviation or the standard error or like the confidence interval. So to summarize, the methods used to compare means depends on the number of compared groups. We said, how do I summarize my data? Like comparing means or proportions, how do I summarize my data? Or how do I analyze my data? So usually the point of data analysis is not only a descriptive one where we tell about the mean and the median of the data. We also want to compare groups. When we want to compare groups, again, whether we have to compare means or whether we have to compare the median depends on some factors. And again, those factors are like the distribution of the data, the scale of the data, and mostly these two are the very important one, and often the sample size. So, and how to compare and what statistics to report also depends on the sample size. For two-group mean comparison, when we compare two groups like female and male, we use students t-test, sample size is small, or z-test, large sample size. So to compare two means for normally distributed data, we report the students t statistics. So the students t is calculated by subtracting the two means of the groups, the mean. So for example, if we are comparing the blood pressure of male and female participant, we will summarize the blood pressure in each group as mean, and then we also summarize the data as standard deviation. We create the standard deviation for each group. And to say there is a difference, significant difference between the two groups, we will take the difference between the two means and divide it by a pooled standard deviation. Standard deviation that's created based on the standard deviation of the two groups. And then we get the t statistics or the d statistics based on the sample size. If the sample size is, say, less than or equal to 30, usually we use a student t-test. If the sample size is greater than 30, we use a z-test. But as the sample size increases, usually they converge, they give about the same information. So for more than two groups comparison, to compare the means of more than two groups, for example, to compare the means of the same blood pressure or say cholesterol by a school, by region, by other factors, which is like more than two groups, we use the analysis of variance. So we are comparing means, but we are making our statistics, creating the statistics based on the variance or the variance of the variable. The variance is the square of the standard deviation. So many people use ANOVA to compare two or more than two groups, usually more than two groups. And so in analysis of variance, we compare the variability between groups divided by the variability within groups. So combining all the data, we get the variability within group. And when we look at the variability between groups, so when we compare the variability or the variance, the between group variance over the within group variance, if it is greater than 1, usually if the difference is very huge, we found there is a significant difference. So based on that information, we can compare meanings between more than two groups. There are many other information. We don't get into the detail about comparing variance. There is degrees of freedom, which is based on the total number of observation and also number of the groups. And that's very important when we calculate the F statistics in comparing groups. Anyways, for comparing two groups, the mean of two groups, we use a T statistics or a Z statistics. For comparing the means of more than two groups, we use analysis of variance, commonly for normally distributed data. So the analysis of variance compares between group variance to within group variance, and it tells whether there are at least two group means different within the compared groups. So for example, if there are group A, B, and C, this may be significant if any of the two mean of the groups are different. For example, if the mean of A is different from that of B, group B, or if it is different from that of group C, or if the mean of B is different from that of group C, the test tells us there is a significant difference. While the null hypothesis is there is no difference between any one of the groups in the group. So how to compare means for non-normally distributed data, like ordinal scale data or non-normally distributed continuous data? We compare ranks or medians. So usually use statistical tests include the glucosan rank sum test or Mann-Whitney test or Kruskal-Wallis test. Again, the first one is used for the glucosan rank sum test is used for comparing two means, two groups, and the Kruskal-Wallis test is used for comparing the median of more than two groups or the ranks of more than two groups. So in this case, the concept is the concept of using the rank sum test or Kruskal-Wallis test is just like we identify data that comes from each group and say give them a different color. We add them together in rank and in the increasing order, and then we separate again. We give them rank. When we add them together, we give them rank and add those ranks based on for a given group. So based on that rank, whether one data is different from the others is determined. So especially like in the glucosan rank sum test. So for non-normally distributed data or data on ordinal scale, we use non-parametric methods like the glucosan rank sum test and Kruskal-Wallis test. And when we say non-parametric, we mean it's not normally distributed. It doesn't come from data with a known distribution. And for such kind of data, we use non-parametric tests like the glucosan rank sum test, Kruskal-Wallis tests. So let's go and do some quiz. So there is a quiz here. I don't know if, let's see. Huh? Yeah, so the instruction says choose the correct answer among the multiple questions. Question might have one or more answers. So identify the scale of measurement for the following categories of disease. So the first one is, we have categories of disease: diabetes, coronary heart disease, cancer, stroke. This is what scale?
Nominal.
Yeah, it's a nominal scale. Identify the scales of measurement for the following measurement. For a measurement on Likert scale.
This is okay. Strength, good, better, worst. Is it ordinary or?
Yeah, it's ordinal.
Yeah, it should be high order. Yeah. There is other goes to
Identify the scale of measurement for the following: blood glucose measured in milligram per deciliter.
It's just some visual. It's a numerical.
It's numerical.
Numerical should be the interval.
Interval.
Yeah, even numerical should be interval. Right?
Yeah, it's interval, but
what's the ratio?
It's ratio. Yeah, there can be true zero. In this case, blood glucose might be 0. Like if a person is hypoglycemic, the blood pressure, blood glucose might fall, might be 0.
So gram per. It's the number should be the numeric number, right?
Yeah, it's numeric number.
Numeric number should be interval is okay too. Oh.
And so the difference between a ratio scale variable and interval scale variable is, for ratio, there is a true zero. True zero means
true real. Okay.
Yeah,
okay.
True zero.
Okay, that's it. So can be blood gross rate can be 0.
Yes.
So interval is no real.
Interval, there is no true zero. Like, yeah.
Scale mirror of the female. Yeah,
identify the scales of measurement for gender.
No. No.
No.
No. Yeah. No.
No.
Yeah. No.
Yeah.
Author do their protect the patient. What summary structure do you use? Summary age can be numerical. Mean is okay.
Yeah.
Standard deviation is okay.
Okay.
Okay, it's median is also okay. Okay, that's problem. How do you describe median?
Yeah. Unless the variable is converted into another form, we don't use proportion in person.
And then we get median or mean for based on distribution, based on scale measurement, it don't matter. You should always use it based on the information you want to say. Okay, based on distribution, based on scale measurement.
Based on scale of measurement.
Also based on information you want to send out.
Yeah.
What needed other? What measure of ability do you report? What other scale? Other media is okay, right?
This is for the measure of variability to report for ordinal scale variable.
Other scale variable.
Measure of variability or measure of dispersion.
Compare. Yeah, they are confused. Standard deviation, no.
Yeah, so
counter range. Inter-counter range.
Yes.
What is the media for 3.5? 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5, and then in the media is 3 and 4.
How many numbers do we have? 1, 2, 3, 4, 5.
Yeah, 5. So media is 1, 2, 3, 4, 5, 3. 3 is the media. Which roughly figure represent normal distributed. Okay, it's good. Good. Normal distribution. Yeah, first no. B is approximately B and D probably.
B and D.
B is not okay. It looks not exactly, but
yes, not exactly. Usually it is acceptable, especially when the middle part of the data is aligned with the line.
It's okay.
Yeah, it's okay. The tail part, there are some outliers, but still this is.
And most of them in the line. Okay, that's Q part. Yeah, most of them. D definitely.
Yeah.
You'd like to compare pre and post corrections B angle with angle. If you want to compare pre and post seizure corrections, being angle or patient, if continuous variable we can mean.
So if you would like to compare pre and post surgical correction of slant angles of patient with vertical dislocation, you will compare mean.
Mean. No, not mean.
Oh, yeah.
Let's see how many we can get. View. Good.
Yeah.
Let's say some go over it's okay. So is the plot, the cuckoo plot is, did you plot using R or SAS?
The QQ in R.
Oh, okay. SAS can also work.
Yeah.
We should have I did use R, but I never use SAS to plot the cuckoo. Check.
Yeah, you can say, for example, when you compare two means, you can ask all data like using t-test. It gives you.
Normally,
gives you
when we calculate mean, the missing data or normally not included.
Yeah, so missing data is one important topic we might cover in the future. Missing data.
Yeah.
Some might want to remove the participant with missing data.
But normally when we calculate, they're not included.
They are not included. They will be deleted at least twice.
Yeah, but sometimes important should probably treat other way. All right, thank you.
Hello? All right.
Okay, thank you. Just stop recording.
Let me see. So we have some upcoming presentations in March. We will start sending out notices. The next presentation will be on the validity and accuracy of tests or models like the sensitivity, specificity, positive and negative predictive values, what they tell us. In April, we'll present study designs, and in May, we will present on the nuts and bolts of regression models, and we'll continue again to present on that. In August, we'll present on meta-analysis and systematic review. Thank you very much. If any person has a question, you can. Let's see. I don't know if anybody attended this.
That's good.